So hopefully everybody survived Halloween okay. Yeah. Just to remind you, the homework assignment due Friday, and then the tour of the cyclotron. So we're all set. We've got people lined up to give us a nice tour once we get there. And again, the idea is to not show up here on Friday, but to meet either at Hearst in front of Corey, and we'll ride the bus up, or you can just walk straight up the hill, and the guards at the gate will know about you and let you in anyway. Okay. And then again, second exam a week from Friday. Okay, in class, the full 2 hours, just like the last one. Okay? Okay. Right. Okay, so on Friday we talked about two classes of detectors. These were all, well, we talked about ionization counters, and then we talked about scintillation type detectors, and I showed you sodium iodide and plastic scintillation detectors, and we talked about the relative merits of each. The plastic scintillators are cheap, rugged. Sodium iodide detectors are more sensitive to environmental issues. They don't like humidity, they don't like water, they don't like being banged around, but they offer much better energy resolution than the plastic. Today we're going to talk about another class of detectors, and I've got one here to try to illustrate the improved energy resolution you can get using semiconductor detectors. And there are two major classes of semiconductor detectors, and I managed to forget one of the things I was going to bring, but okay, based on either silicon or germanium. These are both semiconductor elements, and what that means is normally they act as an insulator, okay? They don't conduct current, but with a little bit of energy you can promote the electrons from the valence band to the conduction band and make them operate more like a conductor. And this table is meant to illustrate some of the relative properties of both silicon and germanium and why they might be useful. And the major thing to look at here is, remember when we were talking about the ionization counters, that it took about 30 electron volts to make one electron hole pair, whereas for germanium it's about 3 electron volts, and for silicon it's a little bit more, 3.6 electron volts. That means for a given amount of energy being deposited in these materials, you create a lot more ionization because it's a lot easier to rip those electrons off either germanium or silicon than it is off a gas molecule in a gas counter, or in order to produce a scintillation photon in either the plastic or the sodium iodide type detectors. It takes a similar amount of energy, on the order of 30 electron volts. So you get a lot more bang for your buck, in a sense, with the silicon and germanium. They also offer some nice properties with respect to photon detection above the plastic or the liquid scintillators, in that they each have higher Z's. So the Z for silicon is 14 and for germanium is 32. And you know from our discussions of how gamma rays interact with matter that whether it's Compton scattering, pair production, or photoelectric effect, the higher the Z, the higher the cross section. And so if you're talking about trying to do the best in terms of energy resolution and trying to do photon spectroscopy with the highest sensitivity, germanium is currently the state of the art. Okay, not that particular detector, but detectors like it. And I'll show you a little bit how good they can do. The silicon detectors have some advantage over germanium if it's charged particles you're looking for. If you're going to look for electrons or protons or alpha particles, silicon is the preferred way to do it. And the reason is that it takes so little energy to make an electron hole pair in germanium. In order to get the best energy resolution you can, you have to cool them to something like liquid nitrogen temperatures. And so this enormous thermos bottle over here is full of liquid nitrogen meant to cool a little crystal of germanium, which is up in here. And so there's a copper cold rod, cold finger, that's coming out here, touching the back of the germanium right here, coming like this and going down into the liquid nitrogen. And so the bottom end of that copper rod is sitting in the liquid nitrogen at 77 Kelvin and cooling the germanium to something close to that. And that's required in order to reduce the thermal excitation of electron ion pairs in the germanium so you can get the good energy resolution. Because it costs a bit more energy to do that in silicon, you don't have to cool silicon. Okay? And so for charged particle detection, that's typically the way it's done with wafers of silicon. And Lilly has some discussion of that in his book. The reason these things work involves a little bit of solid state physics. And this isn't a solid state physics class, but it's important to at least get a qualitative understanding of what's going on here. And typically what's done, at least in the past, is you would dope these materials. So you would take, let's say, silicon or germanium, and drawing it silicon, and I'm sorry, part of it's off the top there. You dope it with a bit of phosphorus, okay? And the point is that the phosphorus likes to lose electrons. And so it is what's called a donor. It can donate electrons rather easily. And this is meant to be the valence band and the conduction band of silicon. And the electrons from the phosphorus are easily donated into the conduction band. There are other kinds of dopants you can put in particular boron. Boron is what's called an acceptor. It likes to grab electrons from other things, okay? And so it can readily accept electrons from the valence band. And you might not think this is useful, but if you put these two together, you put together a part of the material which is doped in this way and another part which is doped in this way and let them come in contact with one another, what's shown in the drawing on the right here, left here tends to happen. That is, the electrons from the donor migrate over to the region where the acceptors are. And this donor type material is called N-type for historical reasons. It has to do with the fact that the things which are moving are negatively charged, the electrons, and the P-type are positively charged, those are the holes. So the donors donate electrons to the acceptors, and you get a net migration of charge. So you end up separating charges. You end up with a positive voltage over here and a negative voltage over here because of the movement of those electrons. And in between, you have what's called a depletion region. This is a region that doesn't have any acceptors or donors. And that's the active region for the radiation detector. Because what happens then if a radiation comes in and produces electrons and holes there, they're free to migrate. And they will migrate under the influence of this electric field which has been set up. And so you'll end up with a current, holes going one way, the electrons going the other way. Now, intrinsically, if you just have the P-type and N-type next to each other, this depletion region where the migration has happened is very, very small. And that means there's a small probability that your radiation will hit that area and be detected. But you can make this region wider by applying an external high voltage. And that's what we're going to do here. So you put an external high voltage V across this, and you end up sweeping the charge out of a much bigger region. And now this becomes the depletion region. And so in this germanium detector in here, this one's about 2 inches in diameter and about 2 inches long. And we're going to put 3,200 volts across it. And we'll create a depletion region which occupies almost the entire volume of that crystal. And so what that means is then when photons come in and interact anywhere in there and produce ionization, we'll sweep the charge out and measure the size of the current signal and get a good measurement of the energy. And a similar thing happens for silicon detectors. And this is meant just to illustrate qualitatively the difference in energy resolution you can get. The broad curve is what you get from sodium iodide, and this was a cesium-137 source, one of the ones we looked at on Friday. The energy resolution, which is a measurement of how wide that peak is, and typically the way it's quoted is what's called the full width at half maximum. And what that means is you go look at the peak and you figure out how many counts or how many events there are in the highest channel number, and then you walk your way down either side of it until you get to half that number, and you count how many channels or how much energy there is in between the two half maximum points. And so it's the full width at half maximum there. And for sodium iodide, it might be something like 40 keV for this particular energy, which means something like 6 or 7% energy resolution at this energy. Whereas for germanium, it's much, much better. You can see the peak is much narrower, and you'll see that in a minute. And it's more like 0.1% or a few tenths of a percent for this kind of resolution. And if you're looking at a single gamma ray, you may not think that makes any difference. And in fact, that's true. If the only gamma ray in the spectrum were this 662, it would be easy to pick it out with sodium iodide. But you'll see in a minute, we often have situations where we have many, many gamma rays, and it's not so easy to tell whether there's 1 or 2 or 100 of them. This is an updated version of what I showed you on Friday. So this was meant to be a potassium-40 spectrum, a 1461 keV photon going into a plastic detector, and we saw that basically you get the Compton edge and nothing else. In sodium iodide, it looks like that. There is a peak there, but it's very broad. And now you do it with germanium, it's almost a delta function. Not quite, but almost. And here, so here's some more. This is a watch that's painted with radium. It's an old-fashioned watch. It was painted with radium so the dials would glow in the dark, and so you could read them in the dark. There's a lot of radioactivity there, and if you bring it up to a plastic scintillator, you see a lot of events, but you can barely tell that there are features in that. It's almost a smooth continuum. If you look with sodium iodide, there's some broad bumps, but if you look with germanium, it's a real forest of gamma rays, okay? Many, many gamma rays. And so if you actually wanted to do detailed spectroscopy and understand the origin of these peaks, you need this kind of energy resolution. And that's why we're willing to deal with cryogenic detectors and all the associated complications of that. Okay, so let me actually demonstrate this and show you that it really does work as advertised. So it's the same data acquisition system we had the other day. What I have to do is, again, to deplete the active region here, I have to apply about 3,200 volts across the crystal. And so we can do that. Adjust the controls. This lets me turn on the high voltage, and I can turn the high voltage on, and you can watch the voltage go up there. I have to be a little bit careful not to turn it up too fast. Essentially, you get sparks, and you can permanently damage the crystal or the electronics, and so you have to go up rather slowly. And what we're doing is we're just increasing that region where the depletion is going on by applying this voltage. There's a little red warning light on the detector that comes on occasionally to tell me I'm going too fast. We're halfway there. $3,200. Okay, it should be happy. Let it. Okay. Now, if I. Okay, so it's counting, and you can see the grass growing. Let's bring over a source. And let's start with cesium-137. And you can see almost the delta function showing up here. Hopefully you can see that. And I can expand that, and we can look at it in a little more detail. Okay, so it's not quite a delta function. What we can do, see if we can, okay, I have to stop it for a second. What I can do is, okay, the program has highlighted this area here and tried to fit it and determine how wide it is. So the calibrate, let's actually calibrate it. Let's go through that. So what the program doesn't know right now is the energy of that gamma ray. And so let's give it 3 gamma rays. We'll calibrate it, and then we can try to identify what's going on. So this is cobalt-60. And it's a little weaker. Let's bring it over here. Okay. Now it's counting pretty fast. So remember, the cobalt-60 has 2 gamma rays, 1173 keV and 1332, and the cesium has 1 gamma ray at 662 keV. And we can use them then to allow the electronics to convert channel numbers into real energies. So if I go back for a minute. Okay, so there's the cesium. We'll do this for the cobalt. Okay. Okay, so now I've got my 3 peaks, And I go up here and I say calibrate the energy. And I'll tell it to forget about it. It has some calibration in its memory. We'll tell it to forget about that. And we'll go over here and tell it the energy of this gamma ray. It's actually 662 keV. Okay. And we'll go over here and we'll tell it this one is, oops, which one is it? Now I don't know which one it is. That's a problem. Come on. Too quick. Too quick. This one. That's 11. It already thinks it's about 1170. What it's doing is it's trying to fit a straight line to a plot of channel number versus energy. Okay, and so we're not too far off. 1332. Bingo. We'll say save it. Yes, fine. Yes. Okay, so now it knows, and if I go over here, okay, close that. Okay. And so now, if we go back, and let's look at the 1332 keV peak. So it's counting nice and fast, and if I ask it to fit it, okay, so what it's done now is it's fit this to a shape. The typical shape in a detector like this is what's called Gaussian, and it figures out that the full width at half maximum is 1.8 keV. So for an energy of 1332 keV, the energy resolution is 1.8 keV. It's about 0.15% in percentage terms. Okay, so it's much, much better than that sodium iodide detector and infinitely better than the plastic scintillators. And this becomes important, as I said, when you've got many, many gamma rays and you're trying to understand what's going on. And just to illustrate that again, let's bring the Fiestaware over. Get rid of those. Clear that out. To make a liar of me. Not so many. That's interesting. That's actually surprising. Okay, I thought there would be more. But let's let this count for a little bit. And we'll come back to it later. Alt 2, Alt 3, Alt 1. Okay, so germanium detectors have much better energy resolution, and they are important when you have lots of gamma rays to look at. Now, one of the, actually, maybe I can illustrate this again. One of the unfortunate things about these detectors is that they are relatively small. And so here's my cobalt-60 spectrum. Here are the two big gamma rays. But this detector is only about 2 inches in diameter and 2 inches long. And what do you think is the most likely thing when one of those gamma rays gets emitted? What's going to happen? You can actually see it from the spectrum. Where are most of the events in that spectrum? It's a little misleading. You're concentrating on these things because they're very tall, but notice that they're also very, very narrow. If I actually count up how many events are in this region, say these two regions, and compare it to here, there are far more events down here than there are in both of those peaks. What's causing that? Is there something wrong with my detector? Is it misbehaving? Or is there some physics going on that we talked about? So these are photons coming out of that source. And what are the three ways they can interact in any kind of material? Compton scattering, photoelectric, pair production. Okay. Now, what's the most likely thing for these particular energy gamma rays, which are 1173 and 1332 keV? Okay, pair production, is that going to be it? Probably not, even though they are energetic enough to produce electron-positron pairs. They're very close to being right at the threshold, and so the cross-section for that process is going to be pretty small. What about photoelectric? They're too high in energy for that for a material like germanium. So that leaves Compton scattering. And that's actually what all this stuff is. This is Compton scattering, okay? Where the photon goes in, scatters off an electron, and that electron then comes to rest inside the germanium. It produces ionization, but the problem is the energy that electron had is not equal to the total energy the photon had when it came in. So you end up with this continuum of gamma ray events that go from 0 up to essentially the Compton edge. And you can sort of see here there are actually two Compton edges because there are two different gamma ray energies here, okay? And that's a feature of all germanium detectors, that even the largest ones today, which are 4 or 5 times as big as this one, still aren't big enough to fully contain much in the way of gamma ray energy. And so they're plagued with this Compton scattering. And again, in a situation like this where we have a very easy to understand spectrum, there are only 2 gamma rays and they're above the Comptons that they produce, it isn't a big issue. However, suppose I had a very complicated spectrum and I was interested in a gamma ray about here, and I had lots of high energy gamma rays that produce a Compton background that those gamma rays then sit on. That's a problem. And when we go up to Lawrence Berkeley Lab on Friday, you'll see a project which is attempting to get around this issue, basically trying to build an array of germanium detectors that would cover the entire surface of a sphere with germanium. And what that would allow is that if a gamma ray went into one detector and Compton scattered, it would then go into another detector, and you could add together the energies and recover the full energy of the original gamma ray. And you'd never lose anything to Compton scattering. That project is called Greta, and there's a prototype called Gratina, which you'll see on Friday. Okay, enough about that. Any questions about that stuff? We talked about the plastic scintillators being cheap and easy to use, and the sodium iodides being a bit more expensive and a little less easy to use. These things are an order of magnitude more expensive. So a detector like that costs on the order of $20,000, okay? And you have to fill it with liquid nitrogen. A doer like that will last about a week. So there's a lot of maintenance associated with it. And if you're trying to do this kind of gamma ray work in the field, that's an issue you have to deal with. There is a new way to cool the detectors. It's an electromechanical system. It's still a complicated beast, and it ends up being even more expensive to do it that way. So if you're thinking about homeland security issues where you'd like to do gamma ray spectroscopy at a seaport or at a border crossing, there are ways to do it with germanium, but it's not trivial. And so very often it's done with simpler systems, just for practical reasons. Okay. Now, we were talking about, we spent a lot of time talking about gamma ray spectroscopy. But of course, that isn't the only kind of radiation we want to detect. And so one other thing that's useful to talk about are neutron detectors. And we talked about the fact that neutrons themselves don't produce ionization. And so we have to allow the neutron to interact. And the way it interacts is via the nuclear force. So it's a nuclear reaction with something, which then produces a charged particle, which can then produce ionization. And so there are a bunch of different reactions which are the basis of neutron detectors, and they're shown here. So for example, the upper curve is the basis of one of the most commonly found neutron counter. It's based on helium-3. So helium-3 is a stable, although rare isotope of helium. You can fill a gas proportional counter with helium-3 gas, and if it gets exposed to neutrons, it turns out the neutrons have a very, very large cross-section. You can see at thermal energies it's thousands of barns, and it falls off like 1 over the velocity of the neutron, as we've seen before, for an NP reaction. So the neutron gets captured on helium-3. It makes a compound nucleus of helium-4, but in a very highly excited state. And that compound nucleus then falls apart, and it falls apart mainly into a proton and a triton. And this is all happening inside the proportional counter. So the proton and triton have kinetic energy as a result of the positive Q value for that reaction. They then produce an ionization signal, which you measure. And so, like I said, helium-3 counters are very often used for neutron detection. You don't get much in the way of energy information out about what was the energy of the neutron, but if you just want to know how many that there were, that's a very good kind of detector. Then there are other detectors. We've talked about this reaction, boron 10N alpha. It was the one that we talked about being useful for boron neutron capture therapy, because you end up with an alpha particle and a lithium-7, which have a lot of energy because, again, that reaction has a very large and positive Q value, and they deposit all of their energy in a very short distance, and so you can do a lot of damage to the tumor if you can manage to put the boron 10 where you want it. You can also make detectors out of boron. Boron trifluoride is a common gas compound which is used in a variety of neutron detectors. And again, it's the same idea. You have the boron trifluoride in a gas and a proportional counter, and when the neutrons interact, the alpha and the lithium-7 produce the ionization that you see. Lilly has a nice discussion about the fact that these curves which are falling like this all follow that 1 over V cross-section dependence. That is, the cross-section as a function of neutron velocity goes like 1 over the velocity. And that has some interesting features in terms of making a neutron detector, because if you think about it, what is the flux of neutrons that's hitting your detector? One way to think of it is it's a number density, the number of neutrons per cubic centimeter, times their velocity. And so if you wanted to know how many events you're going to see in your detector, you would put in a flux and you'd multiply it by a cross-section, okay? Well, the cross-section goes like 1 over V, and the flux has a V in it. Those V's cancel out, and you end up with a neutron detection efficiency which is independent of energy, which is a very important thing, at least in this low energy region where the cross-section goes like 1 over V. There's another kind of detector which is used for higher energy neutrons, and that provides energy information on the neutrons. And it's based on this other curve shown here, hydrogen 1 elastic scattering of neutrons. So you have hydrogen, a neutron comes in and smacks it. These are basically equal mass billiard balls, if you like. We're assuming the proton and neutron masses are sufficiently close that we don't have to worry about that small difference. And so you get elastic scattering of billiard balls. And I think you've been through some homework problems related to this a while ago. And you can calculate the energy of the outgoing proton as a function of the angle using just non-relativistic classical mechanics. And what you find is that the energy spectrum that you get basically goes from 0 up to the energy the neutron came in with. And it just depends on the angle that the proton happens to scatter. If the neutron comes in and hits the proton head on, and the proton goes off at 0 degrees, it carries the full energy the neutron had, and the neutron comes to rest. And that gets you here. And as you go to smaller angles, you fill in the remaining region down there. And so you can then use that as a way to measure the original neutron energy by trying to see where the edge is in your detected spectrum. And this is a spectrum taken with detector based on this recoil proton. Usually it's a plastic scintillator, okay? So the same kind of scintillator we had in here on Friday. It's made of carbon, hydrogen, and oxygen. And the hydrogens then can have this elastic neutron scattering occur, and you get a recoiling proton in the plastic scintillator, which makes a light signal that the photomultiplier tube sees. And if you were sending in 2.6 MeV neutrons, so you have monoenergetic neutrons to start with, theoretically, this is what you should see. Because your detector isn't perfect and doesn't have perfect energy resolution, it's smeared out a bit, but nevertheless, you can see there's more or less an endpoint there, which is correlated with the energy of the neutrons. So if you have monoenergetic neutrons, or at least neutrons that have a well-defined maximum energy, you can use one of these proton recoil detectors to get some energy information. Now, I mentioned that the the detector, the plastic scintillator, is made of carbon, hydrogen, and oxygen. Why don't I talk about the neutron scattering off the carbon and oxygen? Does that not happen? Pardon me? Exactly right. So because the carbon and oxygen are heavier, the neutron doesn't transfer as much energy to them. And as a result, those recoiling ions don't produce much in the way of light. Exactly right. So it's only the fact that the proton is so light that it can recoil with essentially the full kinetic energy the neutron had that I get this kind of response. So the plastic scintillators are mainly sensitive to the hydrogen that's in them. Okay. Now, we've been talking about a general class of detectors that are based on the fact that this radiation we've been discussing produces ionization. Okay? I've been saying that the electrons, the photons, the alpha particles, whatever, when they go into matter through one process or another, ionize the material. Okay? And we make use of that to build our detectors. But there's a whole other class of detectors, and unfortunately my little label is off scale here. It says bolometric detectors. And it uses a totally different principle, and although it's not as widespread right now, these are becoming more and more useful, and I'd just like you to know that there is another way to do this. So suppose I had a crystal. It could be germanium, it could be silicon, it could be any kind of material. And suppose I had a 5 MeV electron enter that material and stop. And it's an insulating crystal and it's not connected to anything else in the world. What happens to that energy? What does that electron do when it goes into the crystal? Pardon? Very good. Very good. Ultimately, that is what's going on. But first, the electron loses energy the way we've talked about before. It ionizes the crystal, whatever it happens to be. The problem is that there's nowhere for that ionization to go. I haven't put any bias potential across it. I'm not collecting the charge. And so the electron ionizes along some track, but those electrons that it's created and the positively charged ions recombine and neutralize the system again. Okay? Does that mean the energy has just disappeared? No, energy is always conserved. Okay? We don't know of any process that violates conservation of energy, so it must go somewhere. And the gentleman who said vibrations is absolutely right. What it ends up doing is heating up the material. Okay? Those electrical excitations initially turn into vibrational excitations we call phonons. And the material actually heats up. Now, normally we don't even think about this because if I have a macroscopic object, say this bowl or my crystal of germanium inside there, and I deposit an MeV or 5 MeVs worth of energy in it, you can calculate how much the temperature will rise, and it's a negligibly small amount. It's an immeasurably small amount, and that's because of what we call the heat capacity, the amount of energy that's required to raise the temperature of an object a certain amount. But if you cool objects very close to absolute zero, that heat capacity gets much, much smaller. And then it becomes possible to actually measure the temperature rise that is produced by radiation hitting it. And that's the basis of these so-called bolometric detectors. And as I said, they're not in terribly widespread use yet, but they're getting there. So the idea behind these is you have some object, and this is the basis of a double beta decay experiment we're working on. And so the crystals we're using happen to be made of tellurium dioxide, but it actually doesn't matter what they are. It could be anything. So you have a crystal, and you cool it very nearly to absolute zero. In our case, we cool it to 10 millikelvin. So this is 0.01 degrees above absolute zero. You use a very complicated refrigerator to do that. And what happens then is that this object, this crystal, has a heat capacity which is so small that if you deposit 1 MeV's worth of energy in it, as an electron, as a gamma ray, or an alpha particle, whatever you want, so you deposit 1 MeV in this object, and I should point out the object weighs about 1 kilogram. It's not something small. It's the size of my fist. If you deposit an MeV's worth of energy in it, you raise the temperature by 0.1 millikelvin. Okay, 0.1 millikelvin out of 10 millikelvin. That's a measurable temperature rise if you have a very, very sensitive thermometer. And so what you do is you attach a very sensitive thermometer to that, and you measure the temperature rise when radiation hits it. You measure it event by event. So the temperature rises for a little bit, and because the crystal is connected to the outside world, the temperature falls back down to its base temperature, 10 millikelvin, rather quickly, but you get a temperature spike, and it turns out that spike is directly proportional to the energy that was deposited. This is actually being done right now. These are the crystals. These are the tellurium dioxide crystals. Each one is 5 centimeters on a side. Okay, so it's a cube, 5 centimeters by 5 by 5. There are 4 of them in this little copper prison right there. This is a blow-up of one of them, and this is the thermometer. This is an interesting little bit of nuclear physics. This is a wafer of very, very pure germanium, which has been irradiated in a nuclear reactor to produce arsenic and selenium and gallium dopants in it in such a way that the germanium now has a temperature-dependent resistivity. And it's glued onto the crystal, and when the crystal warms up, the resistivity of the germanium changes, and what you probably can't see here is there are very, very fine gold wires coming in and going out here. You run a small current through the thermistor or thermometer. You measure the voltage drop across it. When the temperature changes here, the voltage drop changes. You see a voltage spike. Okay? And that's the basis for this. And just to show you how they work, this is a pulse. Okay, it's going off screen. This is time running this way. This is the amplitude. There's a big temperature spike when an event happens in the crystal, and then it comes back down to the baseline temperature. You can see that these pulses are incredibly slow. The pulse lasts for seconds, and that's because this is a thermal process, it's a thermal relaxation, and so you can't count very quickly in this kind of detector, or the pulses will sum up and sit on top of each other, but we're looking for a very rare kind of event, and so if you're willing to count at very low rates, these are very nice kind of detectors. And this is an energy spectrum that we measured with that detector. This is with a thorium-232 gamma ray source. So this gamma ray is at 2.6 MeV. And the energy resolution here is comparable to what you get from that germanium detector. So this is a whole other technology which is not based on ionization. It's based on the thermal properties, that eventually all the energy that the radiation deposits does get turned into heat. And if you cool things down enough, you can see that. You can also see in this detector, they're small crystals again, similar in size to the germanium. So this gamma ray is at 2.6 MeV. Here are 2 gamma rays that are produced as a result of the pair production effect. So this 2.6 MeV gamma ray goes into the crystal. It produces an electron-positron pair. The positron eventually slows down and annihilates, makes 2 511 keV photons. If I catch both of them, I end up measuring the full 2.6 MeV. If one of them escapes, I get a line at 2.6 minus 0.5 or 2.1 MeV. If both of them escape, I get 2.6 minus 1022, 1500 keV. Okay, so this is the first escape, second escape peak. Okay, you'll hear more about these detectors in the future because they're getting more and more applications, not just in nuclear physics, but in X-ray astronomy, medical applications, homeland security, all kinds of things. So it's worth knowing about. Okay, I think we basically talked enough about detectors, and since we're going to the cyclotron on Friday, we want to start talking about accelerators. And so this is supposed to say accelerators, and a bunch of questions. You know, why do we need accelerator? Why are we bothering to go to a place like the 88-inch cyclotron? What's the point? Why do we have to make things move fast? What is it we're going to accelerate anyway? What kind of particles? Charged particles. And what are we going to want them to do? Make nuclear reactions happen. So if I have a charged particle and I'm shooting it at a nucleus, what's going to happen? Depends on its energy, but what I'm getting at, suppose I have a proton. I ripped off an electron from a hydrogen atom, and I want to shoot that at a uranium nucleus and watch what happens. As the proton approaches the uranium, what happens first? Coulomb interaction. And is it attractive or repulsive? Repulsive. So if that proton is moving slowly, what's going to happen? It's going to get not very close to the nucleus, be repelled away. I won't get close enough to have a nuclear reaction happen. Remember, I have to make the nuclei essentially touch for a nuclear reaction to happen. So the whole point of accelerators really is to overcome the Coulomb barrier, to allow a nuclear reaction to happen. That's why we build them. So given that I want to accelerate atomic nuclei to high enough energies to overcome the Coulomb barrier, what am I going to need to allow that to happen? What am I going to have? Pardon? I'm going to have a lot of kinetic energy in my projectile, and what am I going to need to provide that kinetic energy? High voltage, some kind of accelerator, right? But before I can even accelerate it, there's something else I have to do. Huh? What do you mean by isolate?
Well, I mean, if you want to do accelerated proton, you need to get it inside.
Exactly. I need to ionize it. Exactly. I have to rip those electrons off first, or I have to add electrons. The point is that my materials I can get my hands on are all electrically neutral. And it's difficult, although not impossible, but difficult to accelerate electrically neutral particles. So the first thing I have to do is ionize them somehow. Then I have to provide some means of accelerating them through high voltage, or it turns out there are other ways to do it too, and get them moving fast. So that's one thing. But what else do I want them to do? I suppose I've succeeded in ionizing them. I've succeeded in accelerating them. Is that all I want? Why do we want a magnet? To focus them? Exactly. We want them to hit the thing we want. Is that the only thing we might use a magnet for? Yeah. Exactly. We want to be able to define the energy very well. We'd like to know the energy, and we can use a magnet, for example, to do that. Okay, so we want to ionize things, we want to accelerate them, we want to be able to control the energy, we want to be able to vary the energy, because we may not necessarily know ahead of time exactly the right energy to make the reaction we're interested in happening. And we want to focus the beam. So there are all kinds of things we have to think about in terms of picking an accelerator to do a particular task. And as a result, there are a bunch of different kinds of accelerators which are suited for different kinds of projects. So let's go through those. One which is simple to understand, although it wasn't necessarily the first one developed, is what's called a LINAC accelerator. It's a linear accelerator, and it does use high voltage to accelerate the particles. But you'll see that essentially all these accelerators start out with something called an ion source. Okay, so this is an object which allows us to either rip electrons off of something and make positively charged ions, or add electrons to something to make negatively charged ions. And depending on the exact machine, you'll either want positive or negative ions. So for the LINAC, it actually doesn't matter, but typically they use positively charged ions. So there's an object there which produces positive. And the way this usually works is the ion source, for example, could be sitting at some relatively low potential above ground just to get the ions out of the ion source. So maybe it's sitting at 10 kilovolts or so. And in the LINAC design, there are a series of hollow tubes in this direction. And the idea is that you apply an alternating voltage, or radio frequency voltage, across these tubes. And it relies on the fact that, let's say you have a positively charged ion, and I put a negative potential on that first hollow tube. So the positively charged ion is accelerated to the negatively charged tube, but it's a hollow tube. And one of the interesting properties that hopefully you've learned in your E&M class is that if this tube is made of a conductor, and you're a charged particle and you're inside the conductor, what does the charged particle see in terms of electric field? Nothing. It doesn't see the field, okay? It coasts through there, okay? It's accelerated there and it coasts. And so you vary the field, so now you make the next tube negative, more negative than this one. And then as the ion comes out, it's accelerated that way. And you do this with a periodic potential, but the trick is that the particle is moving faster and faster as it goes from tube to tube. And so you want the amount of time between cycles to always be the same. So you want the amount of time the particle spends in the tube to always be the same. So the tubes have to get longer and longer as the particle moves faster and faster, okay? So that it keeps in phase with your RF frequency that you have over here. And so you end up with an accelerated particle coming out the end there. And depending on how long you make your LINAC, you can get arbitrarily high energy particles coming out. I don't know if you've ever been over to the Stanford Linear Accelerator facility. They have one of these which is 2 miles long. Okay? They used to accelerate protons, now they accelerate electrons and positrons down that 2-mile track, and you can get something like 30 GeV electrons or positrons coming out after 2 miles. But that's a lot of real estate, okay, to be able to do that. So that's a LINAC accelerator. For low-energy nuclear physics, there are other machines which are more common. And one of the first ones to be invented is what's called the Van de Graaff accelerator. And it is based on a relatively simple concept that if you have a positively charged ion, so you have an ion source sitting here, and you manage to put it inside a hollow conductor on which you put a high positive potential. So this is my conductor, the ion source is sitting in there. You put a high positive potential here and you create positively charged ions. Those positively charged ions are repelled away from this conductor, and they come out this way. Okay? And the way the high voltage is put on the conductor is with what's called a charging belt. So this is literally a belt, or sometimes it's a chain. And what you do is you spray electric charge onto the belt. It's mechanically transported up here, and then you have a series of electrodes that pull the charge off and put it on the inside of the conductor. The charge migrates to the outside of the conductor and then provides the high voltage. And typically you can charge these things up to several million volts. And so you get several million volts times whatever charge state you manage to make on your ion in terms of the kinetic energy the particle gets when it comes back down to ground potential. Okay, so you create positively charged ions that way, and you have a Van de Graaff accelerator. If you want to see one of these, we've got one in the basement of this building right now in 1140. We're configuring it right now to do a slightly different kind of thing, but the principle is the same. And then the other kind of Van de Graaff is a slightly more complicated version, but it's based on the same principle. This is called a tandem Van de Graaff. And the idea here is you start with negatively charged ions. So you have an ion source, which, is over here. And in this, what you do is you add an electron to something. So you make it negatively charged. And here's my Van de Graaff. Up here is my terminal. I again apply a positive high voltage using my belt or chain. So this is at positive high voltage. I've got negatively charged ions. So the negatively charged ions are accelerated up to here because opposite charges attract. And while they're right here, I play a dirty trick on it, okay? I put a stripper foil, a piece of carbon or something like that, a little thin foil. And as these negatively charged ions come through, they interact with the stripper, electrons get ripped off, and so when they come out the other side, now they're positively charged. And now they're positively charged and they're repelled away from this positive terminal, so they get accelerated a second time. Accelerated once on the way up to the terminal and again on the way down. And because they're accelerated twice, this is called a tandem Van de Graaff. And you can get much higher energies this way because whatever voltage you have here, let's say it's 5 million volts, usually I have a negatively 1 charged ion, so I get 5 million electron volts of kinetic energy coming up here, but suppose I have a carbon ion, suppose it was carbon 12, and after it's stripped, I remove all of its electrons. So now it's a 6 times positively charged ion. I get 6 times 5 million volts or 30 million volts, plus the 5 I had coming up. I get 35 million electron volt carbon 12 coming out. And this is very often used in low energy nuclear physics these days because it provides a nice way to get a relatively large amount of energy into your ion. And we were talking about magnets, so here you can see there are magnets in this. First of all, there's what's called an inflector magnet, and the idea here is that this ion source is adding electrons to God knows what, and maybe you only want carbon, and so you use the magnet to pick out only those particles that have the right ratio of their charge to their mass to make it around that 90-degree bend and go into your accelerator. And when the ions come out the other end, it's not always true that all of them have had all 6 electrons removed if they happen to be carbon. I'll get ones with 5 electrons, 4 electrons, 3 electrons, and so on. And so I'll have a whole bunch of different energy particles coming out here. But for my experiment, I may only want 1 energy. And so again, I use what's called an analyzing magnet to pick out only those particles that again have the right ratio of charge to mass to make it around this curve. And so I end up with a very nicely defined beam in terms of knowing exactly what it was, and I use what are called collimators or slits to define the position very well. Okay? So these are all what are called electrostatic accelerators because they're using a high voltage potential to accelerate the particles. And these are in a great deal of use all around the world. Unfortunately, not at Lawrence Berkeley Lab anymore. This is what we're going to see on Friday. This is a cyclotron. And I'll just spend 1 minute here, and then I'll go into more detail. But this uses a different mechanism to accelerate particles. This is an idea whose origin goes back to Ernest Lawrence in 1929. He came up with this idea right on this campus. And the first cyclotron he built is now up at the Lawrence Hall of Science at the top of the hill. If you're interested, it's about yay big. It accelerated protons to about 1 million electron volts. And it uses a combination of electric fields and magnetic fields in a very, very clever way. If you look down on a cyclotron, it looks like this. There are two hollow conductors that both look like the letter D, and so they're called Ds. So here's one over here. Here's the other over here. If you look at them from the side, they are hollow. So they look like this. Facing each other. So there's a region in here in which the particles move. And the idea is they're copper conductors. So let's say you produce a positively charged ion and you get it to be right here. You put a negative voltage here. That positive ion is attracted towards the negatively charged D. It goes into that slot. So it goes into the slot. There's a magnetic field pointing into the board. You'll see the pole faces. And so once it goes into the slot, because of Gauss's law, it can't see the electric field anymore, but it does see the magnetic field. And so it moves in a circular orbit whose radius is determined by how much energy it has. While it's in the D and you can't see the electric field, you again play a dirty trick. You change the sign of the potential. You make it positive and you make this one negative. So when it gets over here, it gets an acceleration again. It's repelled away from this D, attracted to that D. And you keep repeating the process. So you alternate the electric field with that RF supply in just such a way that every single time it goes across the gap, it gets accelerated. What Lawrence figured out is that if you have a very uniform magnetic field, the time it takes to go around half an orbit is independent of its energy. And we'll go through that on Wednesday. And so you can make a cyclotron so that each time it orbits, it gets a kick, and it'll make thousands of orbits before it gets out to the edge of the cyclotron, where it gets a little kick from this deflector and goes off into your accelerating tubes. Okay? And the one you're going to see on Friday is called the 88-inch cyclotron because it's literally 88 inches in diameter. Okay? And we'll see how that relates to determining the maximum energy it can produce on Wednesday. Okay? Okay, enough for today.